Hello everyone, I'm Jinyao Zhang from UC Riverside, and today I will be presenting our paper, Intel Enabling High Performance and Energy Efficient in SRAM Cryptographic Hash for IoT. And my advisor is Professor Alahe Sadruddini. First, let me introduce the basic concepts of cryptographic hash. The input of hash can be a binary string of arbitrary bit length, and the output will be a multi-bit string depending on the different variants of hash functions. For example, here we are presenting SHA-3 256, which is the latest member of cryptographic hash algorithm family. The 256 means the bit length of the output is 256. And the most important property of cryptographic hash function is the practical feasibility of inverting or reversing the computation, which means we are unable to know the input data according to the output results. Due to this attractive property, cryptographic hash algorithm has been applied in many domains, such as transport layer security, which is used every time we visit a web page, and post-quantum cryptographic, where hash function, especially SHA-3, is used to generate uniformly random outputs, which is also popular in cryptocurrency designs. Here, we want to give you a motivating example to show how important the hash function plays in our life. Generally, hashing can provide data integrity and identity authentication in secure communication. Assume that Alice wants to send a message to Bob securely. First, Alice and Bob should use key encapsulation mechanism to share mutual secret key with each other. Note that in the post-quantum era, the standard KEM is heavily based on SHA-3, which is the latest member of hash algorithm family. And after sharing the mutual secret key, Alice will combine message and secret key to create digest by hashing. Then the Bob will receive the message and Alice's digest, and Bob will use his own secret key to generate another digest. Then the Bob will check whether the two digests are identical. Only if message was not modified in transit, which indicates the data integrity, and the sender had the identical secret key, which indicates the identity authentication, both digests will be identical, only in this situation. And then Bob can ensure that the data is intact and sent by the trusted Alice. And the above is the actual process that happens every time we want to communicate with someone or want to visit a website. We can see that hashing plays a very important role in this process. And when we switch our perspective to the Internet of Things, we found that the importance of hashing comes more prominent. This is because in IoT era, attackers can effortlessly obtain physical access to edge devices. Though we can use hash-based public key infrastructure to guarantee data integrity and in the identity authentication, this brings new challenges for edge devices. Thus, we need a low latency, high throughput, and energy-efficient solution for hashing in IoT devices. However, it is not that easy to achieve them at the same time. Existing dedicated hardware engine shows great latency, but due to the limited parallelism of on-chip engines, the throughput is low. And compared to our design, this method costs more area on chip. So to improve the throughput, in-memory solution is proposed. Though this approach can achieve higher throughput than dedicated on-chip engines, thanks to the in-memory computing, the latency is not satisfying. This is mainly because this solution is for general purpose computing, which sacrifices performance for flexibility. Moreover, compared to our proposed design, this approach costs more area on chip due to the relatively complicated near-memory logics. Recently, a dedicated in-memory acceleration design is proposed, showing lower latency and higher throughput. However, Such performance improvement is achieved by replicating the memory areas in each stage and the pipeline, which increases a lot of area overhead. In addition, in this method, many different size areas are used to fine-tune the algorithm, which sacrifices most flexibility. Thus, so far, we have not found a method with low latency, high throughput, energy efficiency, and low overhead at the same time, which is essential in IoT era. To achieve these goals, we propose the in-HEL architecture, an in-SRAM on-chip hash design. Since in-HEL is an in-SRAM design, it can either be integrated into a computer system by repurposing the last level cache, or it can interact with the last level cache and the processor as a separate computing cache. This allows in-HEL to have the same level of security as the on-chip engine. In-HEL uses bitline computing to repurpose six transistor SRAM subareas into active large vector computational units to perform hashing on chip, which provides high throughput. We have also carefully designed the data organization for shift-intensive applications, such as SHA-3 in this paper. By placing data structure lengths in different rows and implicitly performing inter-lane shift operations via the controller, most shift operations can be replaced by control commands, which reduces much latency and energy. Furthermore, by combining this shift-optimized data alignment with the proposed in-place rewrite strategy, memory capacity can be greatly reduced, which can accommodate a broad range of SRAM array sizes on a wide variety of IoT devices. Ultimately, in-HEL can achieve up to 14 times throughput per area and 172 throughput per area per energy than state-of-the-art. Next, I will briefly introduce the design of each part of in-HEL separately. We use bitline computing technology from the paper Compute Caches. By activating two word lines at the same time, logical operations such as NOR and AND operations can be performed inherently. Moreover, by adding the next NOR gate to the sense amplifier, we can also implement XOR operations as shown in the figure. Finally, in-HEL can support all the SRAM computing operations in SHA-3 and can also provide massive paradigm to applications. We also propose a shift-optimized data alignment for shift-intensive applications such as SHA-3. Let me first introduce the special data structure in SHA-3 algorithm. Such 1600-bit state is where all the operations occur. The blue part is the 16-bit LAN, and for your information, in the algorithm, there are intensive inter-LAN shift operations and some intra-LAN shift operations. In previous solutions, different LANs will be placed at the same row, which is hard to perform inter-LAN and intra-LAN shift operations. Or all the 1600 bits are placed at the same column. Though all the inter-LAN and intra-LAN shift operations can be implicitly performed via the controller, latency for computing one single state is unaffordable, at least 10 times of the former solution. Therefore, to tackle this problem, we propose a shift-optimized data alignment by placing different LANs into different rows. We can see here, LAN A and LAN B are respectively at the first and the second row. In such 32 times 256 SRAM subarray, we can place 4 independent LANs at the same row. And since these 4 LANs are from different messages and independent, they can be processed parallelly using the in-RAM in-memory computing. The detailed data alignment is at the right figure. Because we put different LANs at different rows, simply choosing different rows equals inter-LAN shifting, which means inter-LAN shifts can be implicitly performed via the controller. And for the intra-LAN shifts, small shifters are used. Compared to multi-stage shifter or 320-bit large shifter adopted in previous solutions, using small shifters is much cheaper, no matter for the area overhead or latency overhead. Thus, our proposed shift-optimized data alignment can well balance the performance and overhead. Despite the data organization, we also propose an in-place rewrite strategy to be combined with the optimized data organization to save memory capacity and maintain the generality of our design in varied IoT devices. Here we give an example to show how this rewrite strategy is applied to a single round of SHA-3 algorithm. First, we need to perform 4 times extra operations and store the results in the last row, CT4. The inputs here are 4 lengths. And in the next time slot, we need to use this CT4 as the input and generate CT4 star. Then in the third time slot, we do the same operation as we did in the first time slot and store CT1. Now we are going to perform in-place operation, using CT4 star and CT1 as the input and store the final result FT at the location of CT4 star. And by our careful design of rewrite order and allocations, more than 50% of intermediate rows can be saved, which is helpful for our design to be deployed in varied constrained IoT devices. Here, we show the overall architecture of InHale. As you can see, InHale is designed as on-chip to ensure high security level and flexibility. The SRAM bank has 2 types of subarrays, data subarrays and control subarrays. The data is placed in common data subarrays, while control commands are stored in control subarrays. We have also specified the control commands in detail. By proposing shift-optimized data alignment and in-place rewrite strategy, the latency and area overhead can greatly be reduced. Also, thanks to bitline computing, the massive parallelism of SRAM can be fully utilized, bringing high throughput. Here, we want to explain our evaluation methodology for InHale to extract rewrite and write latencies for different configurations. We first use PyMTL3 and OpenRAM to generate SRAM arrays, and then using Synopsys design compiler to output latencies. As for the ReRAM latencies, they are generated by Destiny Simulator, which is designed for modeling emerging 3D NVRAM and EDRAM caches. The area and energy numbers are simulated by Destiny Simulator 2. And to decouple the area overhead from the technology node, the metric kilogate equivalent is used. Then, for apples-to-apples comparison between different designs with different memory technologies and processing nodes, we evaluate all the configurations of different designs to make the evaluation complete. Here's the comparison of different designs. Note that the differences between opt and flex is the array size. The opt design has 32 rows, which has higher performance, while the flex design has 250 rows, which has higher universality for common devices. Generally, in-memory solutions are better than ASIC or FPGA designs, especially in terms of throughput and energy. This is because the in-memory computing can exploit the massive parallelism of memory array and reduce unnecessary data movement between processing elements and memory arrays. And among in-memory solutions, our InHale can outperform Recryptor in terms of latency because our InHale has higher frequency with minimal modification to conventional SRAM. When we compare our InHale to Shine, we found that Shine has lower latency. This is because Shine uses dedicated multi-bit XOR logics to improve performance. However, this will greatly introduce extra area overhead. Thus, in metric throughput per area, our InHale beats Shine due to the much smaller area. Compared to Shine, InHale has up to 70 times fewer memory cells and 131 times peripheral logics. Moreover, since InHale performs all the computation within a single subarray, the intensive data movement between subarrays is reduced, which leads to the energy reduction compared to Shine. And within the InHale designs, the opt design generally has higher operating frequency. This is because the data access time is reduced with fewer rows in bitline. We also evaluate the throughput of different designs with or without power constraint. With power constraint, we can see that with the increasing of parallel short-tree number, the design with the highest throughput among all the designs will be changed from shine-to ReRAM to in-hair opt ReRAM. This is because Shine design has higher energy consumption than in-hair design, so Shine will hit the power wall much earlier than the in-hair design. On the other hand, if there is no power constraint, the Shine-2 ReRAM will be comparable with in-hair opt-SRAM because there is no power wall at all. However, in reality, especially for IoT devices, their power budgets are very tight, which means in-hair is the best option for IoT compared to other devices. And in conclusion, in-hair provides high performance, energy efficiency, low overhead, all by proposing an in-SRAM hashing engine. And the shift-optimized data alignment and in-place rewrite strategy are proposed to efficiently map the algorithm into the in-hair architecture. In-hair can also achieve up to 14 times throughput per area and 172 throughput per area per energy than state-of-the-art. And our future work is providing an end-to-end solution for IoT security. I'm very glad to be here. Thanks for your listening.